I would really appreciate, of course, if as the lesson starts, you all turn your cameras on, or as many of you turn the cameras on as possible, as that makes the lessons so much more interesting. I can at least look at you and see your reaction. Good, guys? So please consider turning your cameras on. Please consider participating in this class. Good. So before we begin, several things I would like to remind you of, guys. You all remember my syllabus, correct? And I presume all of you are registered for the My Open Math. All of you are registered, correct? I'm not assuming wrong. I haven't yet checked, but let me remind you guys that you will not be able to take the final exam without being registered to that platform. So make sure absolutely that you are there, and do that fast. You never know if there will be problems later on. Good? All right, guys, welcome all of you that you're just joining. Again, I repeat, please be sure that you are registered on the My Open Math website, because that is your final exam. It goes through that My Open website. Another thing, be sure that you receive emails from me, that you're on my mailing list. Good? Wonderful. Then let's begin the lecture. You all know that you can find all the information on my website. Just look at it. My website is etkin.com. That's where you see the syllabus. That's where you see my email information and my open math information. Let's go on, guys. So this is what we covered last time. Do you remember that we have two definitions? On my mailing list, you should have Zakaria, so write an email with your first and last name and mentioning that you are in the morning section, and write the email to Arkady Etkin at yahoo.com. Good? And Zakaria, you should know about my website. That's the thing about it. On my website, you have prior exams and you have this course information. Wonderful. Back to the lesson. You remember, guys, that two logically identical but psychologically different definitions of the derivative. So you have one definition of the derivative, which we tended to use many times. That's limit as z goes to x of f of z minus fx divided by z minus x. Here again, I try to convey the idea that 2 points are merged together. I can convey that idea by saying that the point z that merges towards the point x looks like x, but is slightly different. And I can use this definition. Okay, they are logically exactly the same. You understand, guys? It's just like reading. You're reading a sentence and you understand what it conveys. That's what you're up to. They are logically the same, 1 and 2, but they are psychologically not the same. One statement will inspire one line of thinking, another statement might inspire another line of thinking. And for non-algebraic functions, the second definition is better. And this is what we did to try to establish the derivative of an exponential function. We said that if we write limit as h goes to 0 of a to the ax plus h minus ax divided by h, you can factor out a to the x plus h into ax, ah. And then you can just factor out a x all together, and you're left with this. And then you recognize, guys, you see that's the point here. You recognize that this part is just the definition of the derivative of the exponential at 0. And that tells you that the derivative of an exponential is not very different from the original function. It's an exponential multiplied by a constant. Are you with me so far, guys? Good. Then we played with a calculator. You see what we did? We tried to figure out what this limit is, but we did not do it exactly. So we played with a calculator, and we decided instead of pushing h to 0, we are going to plug a number that's close enough to 0 and hope that this fraction is a good estimate to what the limit is like. And then we have that I just decided that 1 over 1,000 is a number that seems to me close enough to 0. That's completely subjective, right? There is no reason that maybe 1 over 1,000 is not a good enough estimate at all. But then with 2, I see that this constant looks like it's less than 1. With 3, I see this constant is slightly more than 1. And by toying with the calculator, you might have predicted that there might exist, that's a hypothesis, right? A number e between 2 and 3, where the limit will be exactly 1. You understand why did you want the limit 1? It all should be flowing naturally, guys. If the answer, if this number is 1, then the derivative of the function is the function itself. There is no change, correct? And if there is no change, it's very easy to take derivatives. If you don't believe me, guys, if you take the derivative of 2 to the power of x many times, you will have to multiply 2 to the x many times by 0.693. Do you understand what I mean, guys? Just again, what does this boil down to? So the derivative of 2 to the x, I will say equal, but really it's approximately. It's approximately equal to what? To 2 to the x times 0.69. Yes? Now, I will take the derivative of that. And if I take the derivative of that, it's just the derivative of 2 to the x times the constant. So that means I have 2 to the x times 0.69, but squared. You understand? Multiplying 0.69 by itself, it's not that pleasant. And if you have to do it many times, it's not that pleasant. What's very pleasant is to multiply 1 by itself, because you don't have to do any work, correct? You understand how that works, guys? If the derivative at 0 is 1, then this number is 1, and you don't have to worry about squaring, cubing, and taking it to higher powers. And that's what we have here, guys, right? So we make the realization that we hope there is a number between 2 and 3. We call that number e, such that this limit is 1, because if that limit is 1, then the derivative of e to the x is equal to e to the x. Now I'm going to try to explain to you something extremely significant in mathematics. It's not difficult if, of course, you understand what I'm talking about. So e to the x, guys, I'm trying to find a way to calculate it, right? I'm trying to figure out how to calculate that number e even. If I believe it exists, how do I find it actually? What do I do if I don't have a calculator? How does the calculator carry the calculation? So, and many, many other things. So, guys, is e to the x a polynomial? Do you understand my question? First, guys, even before you answer, do you understand what am I asking you? So is e to the x a polynomial? So some few people say yes, yes. So explain to me when you're saying yes, you mean yes, you understand the question, or yes, it is a polynomial? Yes to both. Okay. Let's look at it carefully, guys. So why would you say it's a polynomial? Guys, remind me, please, and I really need you to remind me. What is a polynomial? When you say e to the x is a polynomial, what are you saying? Okay, Nushin, thank you for mentioning. It has multiplication and addition. Thank you. Only does this mean that e to the x is a polynomial? What makes you conclude that? So for example, if I take e squared, right, that means e multiplied by e. It seems I'm only using multiplication, correct, guys? But look at it. If I even say e cubed, do you see that I don't use multiplication the same number of times? You agree? In a polynomial, once you have the input, you always use the same operations, always the same operations. You don't have one time when you use a few multiplications, another time when you use a lot of multiplications. So when you have the polynomial form, notice another thing. You're not only using multiplication and addition, but for every input, you're doing the same operation with the input, right? So for example, you see, look at this, px equal to 1 plus 5x minus x squared. Do you see what you're doing? That means you're always taking 1 plus 5 times the input minus the input squared. Right here, it's not quite the same operations, and that's only one part of the problem. What about e to the power of 1/2? We mentioned that that means root of e. Right? So when you take roots, it's not at all clear that we're using multiplication or addition, because if it were so clear, you would right away tell me what's root of 5 or what's root of 7. Yes, you can just guess that root of 25 is 5 because it's 5 times 5, but what is root of 7? What is the mechanism by which you can actually carry the calculation? And it's even worse. Expressions of the form e to the power of, let's say, root of 2 are also defined. But what is e to the power of root of 2? You multiply e by itself root of 2 times. What does it even mean? There are all sorts of problems here. Good, guys? Do you understand what I mean, right? So this function is not at all very well understood. Do we have a quiz? Well, I mean, not right now. I'm just talking to you, seeing if you remember something from previous class. Good. Now, you see, I'm hoping that I can express this. What if I have the function f of x equal to e to the x? What I believe about this function mathematically, guys, right? I believe about this function that what is f of 0? That's the one easy value to evaluate. F of 0 is what? 1. Do you all understand why f of 0 is 1, guys? Right, remember that idea with exponentials. When you have a to the 0, you can think of it as a to the power of 1 divided by a to the power of 1. And if a itself is not 0, they cancel out and you have a to the 1 minus 1, right? This result is supposed to be then 1. Because or the cancellation, you see, a non-zero number divided by itself is 1. That's so we are expecting f of 0 to be 1. And the other thing we seem to imagine about this function, we can almost do it abstractly. We can forget about the hypothesis of what e to the x is, even if you want to, right? And we ask ourselves, is a function whose derivative equals to the function itself a polynomial? Do you understand my question, guys? Do you? Right, we are assuming that the derivative of e to the x is the function itself. And we're assuming that at 0, the function equal to 1. Are you with me so far, guys? You see, we're being a bit abstract, but I hope you understand entirely what is my goal here. I think, okay, e to the x, what seems to be so special about it? It seems that it might be a hypothetical function. We haven't even found it. You see, I said hypothesis, e is some number that this limit equals to 1. I'm actually going to go entirely around that limit, and I'm going to figure out a function whose derivative equals to itself. My first question, therefore, is it a polynomial? Well, let's look at that. We know how to take derivatives of polynomials, right, guys? So could a function like this, could it equal to a polynomial of degree 2? So for example, a0 plus a1x plus a2x squared. Could that be true? Remember this f, when you take derivatives, the derivatives don't change the function. Could that equal? Well, let's see. So I take the derivative of f of x, I get f of x by hypothesis. But if I take the derivative of the other side, what do I get? I get a1 plus 2a2x. And if I call this p x, right? So that's p prime x. And if I take p double prime x, what do I get? I get 2a2. And if I take p triple prime x, what do I get? I get 0. But the other function is just not changed by derivatives. Are you understanding what I'm saying? So I see very simply that that it cannot be a square function. It cannot be a quadratic because quadratics are depleted by derivatives after 3 attempts. After 3 derivatives, the quadratic disappears. The quadratic disappears, but this function is not disappearing. Yes? Okay, guys, so pay very close attention. So is it a polynomial of degree 2? No. Could it be a polynomial of degree 3? Tell me, please. No. Tell me why it cannot be a polynomial of degree 3. You understand what I'm asking, guys? I'm hoping that for a function whose derivative is itself, I can find a polynomial expression, since those are the nicest expressions we can hope for. It's going to be 0 after 4 derivatives. A polynomial of degree 3 is going to be 0 after 3 derivatives. Polynomial of degree 4 will be 0 after 4 derivatives, after 5 derivatives, I'm sorry, right? And so on. You understand? If you take derivatives of polynomials of degree 3, take 4 derivatives, the polynomial disappears to 0. But this function never reacts to derivatives. Good? That's what we are doing here, guys. You see? Here I'm showing that same thing. Look at it. Px, p prime x, p double prime x disappears, but the function stays the same. So e to the x is not a quadratic. It is not a cubic by the same reason. And it's not of any finite polynomial degree, right? Because if the polynomial is of degree million, just take 1,000,001 derivatives of that polynomial, it disappears. But this function never disappears. It never changes after the derivative. It stays the same. Are you with me still? Now the leap of faith, guys. You see, what did I find? Notice I underlined. Okay, the function f prime and on, that's just, we're just doing something, we're trying to understand with pure theoretical, we see when we try to take derivatives of exponentials, we see that the derivatives of exponentials are not changed too much from the original exponential function, yes? And then we are hoping that we can find this mythical unicorn, this creature e to the x that doesn't change at the derivatives at all. You understand? If I take derivative of 2 to the x, it's almost 2 to the x. It's 2 to the x times roughly 0.69. If I take the derivative of 3 to the x, it's roughly 3 to the x times 1.099, right? We are thinking that there might exist an exponential that if you take its derivatives, then it will always be the same function. It will be the same. We think that the derivative of e to the x is e to the x. And you understand, guys, we're doing it rather informally. It's just a sort of insight that we're hoping that we understand enough what exponential functions do. It's not true. If you go to analysis, you have to be very precise about it. But that playing with exponentials inspired us to investigate functions whose derivatives are the same function. Derivatives don't change the function. Are you clear? Because we studied derivatives of exponentials and the result is that the derivative is essentially the same, we go through the study of functions that are not changed by derivative. Those are very important functions. You understand, guys? Let me try to give you a very rough philosophy of why those functions are so important. Guys, imagine that you are a ghost hunter and you come to a house and there's poltergeist. You know what's a poltergeist? It's a German word, poltergeist. Right? So, you know, things are flying. You know, the chair is on top of the piano or the piano is on top of the chair. Right? Everything was moved around. You understand? The windows are broken. The dishware is on the floor. If you want to understand this poltergeist, do you know what you pay attention to, guys? not where the most terrible changes happened. You'd pay attention to what was not touched. Imagine that you see that a family photograph, everything was destroyed, but the family photograph was not touched. Are you following me? If you are a clever investigator, you are not impressed by the huge changes. You are impressed by the fact that something was not touched. It reveals the character of the poltergeist. You understand? So our poltergeist here is the derivative. Now, we want to understand which functions it doesn't touch. The derivative touches polynomials. You agree? If you take a finite polynomial, the derivative changes that function. In other words, just to see that very, very vividly, just take 5 derivatives of a degree 4 polynomial and it's 0. Take 7 derivatives of a degree 6 polynomial and you get 0. Clearly? Take plus 1 derivatives, if the polynomial is of degree n, take n plus 1 derivatives, and that polynomial disappears. So what might be a function that the derivative doesn't touch? That's what we're asking. And inspired by this idea that it might be an exponential, I'm going to make additional statement that at 0, the function equals to 1. Because a to the 0 is 1. You understand? So I'm making 2 requirements. I'm saying, let me consider functions that at 0 equal to 1. And aside from that, the only other thing I know is that they are not changed by derivatives. Clear? Right? And if you're curious how is that used, I can show you later. It's not, I mean, you can understand many interesting things in physics if you consider this problem. But you have to understand what's the goal right away, right? So it cannot be a finite polynomial, guys. But could you tell me, let's see, you really want, right? You really want the function to be a polynomial. It cannot be a finite polynomial. Therefore, you're forced to consider the possibility of what? Can you guess? Any ideas? I cannot have a finite polynomial. In other words, I cannot express this function using finitely many additions and multiplications. Then I want the function to be what? Guys, again, turn on your cameras. I don't like the tendency that fewer and fewer of you are showing your faces, right? It would soon come to what? To what? One face? I'm sure that more than the people that are on here could turn. So for example, Marva, maybe you would turn your camera on. Vildan, are you there? Can you turn the camera on? Junaid, Elisha, Francis, Noshin, all of you can, Tzvi, all of you can turn the cameras on so I can look at your faces. Okay, Christiana, I refuse. Okay, well, ein Verweigerer, well, okay, fine. Remember only one thing, guys. Prepare to present your continents for the final in case I decide to, implement it, right? So you should always be presentable to place your head on the chopping block if you have royal blood, right? I present my face on the chopping block. Sure. It would be funny, right? If Anne Boleyn said, I can't today, I don't look pretty enough. All right, let's continue. Thank you guys for turning it on, those that did. Now let's continue. Please tell me, if I really want it to be a polynomial, what, and it cannot be a finite polynomial, what leap of faith do I make? Infinite, Christiana, you got it, right? That's the very difficult leap of faith to make, an infinite polynomial. Now let's try to understand what an infinite polynomial looks like. Exactly, but how do you make that? You should watch Indiana Jones, It looks like a precipice, but you just jump. If you're a man of faith, at some point you jump. And if you're a smart man of faith, then you jump at the right moment. Okay, here we go, guys. Do you see this? So this is my assumptions. I'm going to make it an infinite polynomial. I'm going to say this function is, look at it. It just does not have a biggest power. You understand? It's a0 plus a1x plus a2x squared, so forth. Good? Now, just to help you guys, I want to remind you of the factorial definition. So what is n factorial? N factorial means multiply all the integers until you get to 1. So for example, 3 factorial is 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. Clear? So factorial, just multiply the numbers from where you stand all the way until you get to 1. So let's try to understand, guys, if this is an infinite polynomial, let me try to find its coefficients, because once I know the coefficients, I know the function. You agree? So all I know about this function is that f under derivatives, it doesn't change. Here is that statement. And at 0, it equals to 1. So look what I can do, guys. I can annihilate all the x's by plugging 0. I plug 0, it all disappears. And so a1, the first coefficient has to be 1. Are you with me? Plug 0, the first coefficient has to be 1 because f of 0 is 1 by our hypothesis. So I figured out the first coefficient. Would anybody suggest how? Look at this thing. What should I do next to figure out the second coefficient? We don't have to be fully formal, but what might you do? And notice the function, it's very obvious what you should do. The function, you know nothing about it, only that at 0, it's equal to 1. And you know that the derivatives don't change the function. What do you do? How do you find the next coefficient? How do I find a1? Guys, there are not many options. This function, you know its value at 0. That's all you know about it. And you assume that under derivatives, it doesn't change. So what do you do? What do you do? We already plugged the number, Francis. We plugged 0. At 0, it annihilated all the x's. So the constant term equals to 1. How do I find a1? What next do I do? Yes, Christina, that we figured out. And that's how we figured out that a0 is equal to 1. I'm giving you a huge hint, guys. There is not that much you can do here, right? The function, we don't know anything about it, right? But we know at 0 it's 1, and we know it doesn't react to derivatives. It stays the same. So what do I do? Marika, thank you. But plugging 1 will have all the coefficients, right? And I don't know what's the value of the function at 1. I only know the value of the function at 0. Come on. Very simple, guys. Come on. What's the step that you're making? No, the fork is for your mouth. It's not for your eye. Guys, no. Okay, I really want you to get it. No. Okay. No, then here I'll tell you what you do. But it's when you hear it from you think, my God, how didn't I know that? It's so obvious, right? You take the derivative. Take the derivative. My God, derivative. That's the only thing you can do, guys. My God, what you can do with this function? Just plug 0 and take derivative. So you plug 0 already. Now take the derivative. All right. Now let's see what happens if you take the derivative. Look at it, guys. Here, I take the derivative, it will not be changed. Do you agree? It's the same thing. But if I take the derivative of the polynomial, naturally, I'm assuming that taking derivative of infinite ones is the same as doing it for finite polynomials. That needs to be justified, but you don't begin with justifying. You first you just take a flight of imagination. Look at it. You take the derivative. What happens? This disappears to 0. What happens here? You get a1. What happens here? You get 2a, 2x. What happens here? You get 3a, 3ax squared. Are you with me? And in general, n, a sub n, x to the n minus 1. Are you with me? And now look what happened, guys. Now a1 is the constant term. Do you understand that because the function didn't change? Look at it. I took the derivative. I'm now with the same function, but now it is equal to a slightly different looking polynomial. Different looking, but it has to be the same. So what do I do now? Now I can plug 0. Do you see that? I plug 0, everything is annihilated except a1. So I see that a1 is equal to 1. Are you with me? what do you do next? You see, I figured A0, I figured A1. How do I figure the next term? I did plug 0 before, but if I plug 0 before, only A0 survives. If I plug 0 before, only the first coefficient survives. Now I see that I figured out the second coefficient. Now help me figure out the next. Right? You take the derivative again. You understand, guys? It must be, obviously I could tell you what to do next, but you have to figure it out yourself, right? Just have to feel the subject. That's the entire point. You see, nobody cares if you memorized how to take derivative of something. It's completely useless. I mean, you should be able to think using this material. Then I taught you something. Otherwise, waste of time. Good, so I take the derivative again. Do you see what's the derivative again? Look at it, be careful, guys. Look at it, what happens? This is a constant, disappears, this loses an x, this becomes 3 times 2, you see this. And the function didn't react, it's still equals to x. So now I plug 0 in here. What do I get? I get that 1 equals to x0, but this time it's 2 times a2, which means a2 is 1/2. Are you clear? Look what we have. Look at what we have just figured out so far. We are already observing that the function f of x is equal to 1 plus 1 times x plus 1/2 times x squared, and onwards we don't yet know. Do you follow? 1x, 1/2 x squared. I am filling in the coefficients. I'm figuring out what those coefficients are. So what is A3, guys? So next, now your turn, guys. Calculate A3, please. Tell me what's A3, and the best thing you can do is tell me what's the general term. So Humira says 1/3, Christiana says 1/3. Okay, Zachary says 1/6, good. Be careful, guys. Do it if you want to from the beginning. When you go home, see if you can derive that idea. It's extremely powerful. You cannot even imagine how many things you can do with it. I use it all the time. You see this? This would be the term here. Look what happens, guys. If I take third derivative and I plug 0, I will get 1 because the function doesn't react to derivatives. But the polynomial side of this function equals to 3 times 2 times 1, which is 3 factorial times a3. So a3 equals to 1 over 3 factorial, or 1 over 6. You follow? So it goes, the first coefficient is 1, second coefficient is 1, third coefficient is 1/2, or 1 over 2 factorial. It's really 2 times 1. Third coefficient is 1 over 3 factorial. What do you imagine will be the fourth coefficient? Exactly, Robert. But of course, you need to verify it. So guys, here is the general situation. Do you see? How can I get, can you see it? Can you imagine, guys? How do I get the nth coefficient? I need to take n derivatives to eliminate the x next to it. Do you agree? Can you see it, guys? I can only focus on the nth coefficient, because the other coefficients, if I take n derivatives, the coefficients prior to that will disappear to 0. You agree? Right? If I have x to the 5, if I take 5 derivatives, so x to the 5 derivative would be for something x to the 4, another something x to the 3, x to the 2, x to the 1. Do you understand? If I have x to the 5, take 5 derivatives and there is no more x. Yes? So what happens in general, guys? Let's look at it at the board. So in general, guys, if I want to figure out this coefficient, look at it. I ignore everything from before, right? And that's my function f of x. Right? Tell me, so I take how many derivatives? Look at it. I take n derivatives. You agree? So this is the way I write n derivatives of x. What happens if I take n derivatives of this expression? So first derivative would be n x to the n minus 1. Next derivative would be n minus 1 a nx to the n minus 2. Do you see what happens, guys? You always bring that power down until what's left is x to the power of 0. So what you have is n factorial an x to an. That's it. It's very simple. How do I solve, Francis? I just take the derivative, and then I have stuff afterwards. I just take derivatives. I brought it and made it the constant term. Do you agree? So for instance, if I want to focus on the fourth term, so this is a 4x to the 4. What do? I take the derivative, and that would be 4a3. Next, it would be 4 times 3 a4, that's x, right? X squared. Next, sorry for the space, it's 4 times 3 times 2 a4x to the power of 1. Next, it's 4 times 3 times 2 times 1. Yes? A to the 4. Very simple, extremely simple. If you just I just keep taking derivative, and then once this coefficient is by itself, you see what happens, guys. If it's a to the n, I've taken n derivatives. It's exactly the moment where there is no x next to the nth coefficient. Everything afterwards has an x, and everything before disappeared to 0. Are you clear? It's super simple. Yes? Isn't it super simple? My God, what's happening here? Just take derivatives of a polynomial, right? What's there to think about, really? It's the formulas kind of are melting from your tongue. Good. So what happens is this. Here is that thing written. I plug in 0, and what do I get? I get that if I plug 0, the result is 1, and the equation is n factorial times an equal to 1, which means a sub n equals to 1 over n factorial. Yes? Isn't it amazing? Isn't it amazing, guys? Now you see, if you just have a little bit of insight, you know quite a lot about it. Now, the function that I obtained, here is the way it looks. Look at it. It's 1 plus x plus 1/2 x squared plus 1/3, 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th, and onwards. That's my function. Does it work? Let's look at it. I take the derivative, I get the same function. You see, I take the derivative once, and I get f of x. Yes, it does. And guys, this must be e to the x. Do you know how I know it must be e to the x? There cannot be other option. Think about the rigidity of it, right? So if a curve is built up of line segments, the only difference about the slopes, I mean, when you report all the slopes, that tells you the relative position of the line segments to each other. Do you agree? Do you understand what I'm saying? Let me try to draw it for you if you don't. You have to have a sort of insight, guys. Think about what we do with derivatives. We are trying to say that differentiable curves are like a chain of microscopic line segments. You agree? When I think of differentiable curves, when I say, okay, this curve is differentiable, do you know what I think in my head? I think something like this. I think segmented. I wrote spaces just because I was lazy to connect them. But yeah, I think of segmented line segments. Yes. Now, when I report derivatives, I report the slopes of those line segments. So you understand? This slope, next that slope, next that slope, that traces the shape of that object. And the only thing that can be different is that the shape of that object can be, if it's for the same x, it's right over the same place over the x-axis. But the only thing you can do, you can move it up or down. Moving it up or down will trace the same curve. Are you with me? You understand that? Look at it. Here is a curve. Here is another curve that has the same derivative. Here's another curve that has the same derivative. Right? Those curves have the same shape. Derivative reports the shape of the curve, not its position. right? Not only that, derivatives actually, the way they are presented for this x, that's the derivative. So derivatives represent the shape of the curve over the same x values. Which means, you see, if you reason geometrically, guys, if you have intuitive reasoning like this, you right away know that no matter what it looks like, it must be e to the x, because e to the 0 is 1. You see, as soon as I know one point, I know where this the curves are parallel, right? So once you specify one position, any other curve either does not intersect the value 0, or if it intersects the value 0, it must match that curve if it's the same derivative. Are you with me? What I'm saying is nothing formal. I'm just that's something that you can reason if you understand what the derivatives are talking about. Questions, or you're so bewildered you don't understand anything I say? The formula that I create, guys, for the derivative is, what is it saying? It says for this x, there is a particular slope. So that means that if I know the slope, I can reconstruct the orientation of the line segment. You agree? If you say, for example, for this if I say that the derivative of the function equals to 2x, it's twice the position of x. So I know the position of x. For that position, the slope is twice as much. For this other x, it's twice as much. So I have a sequence of line segments that connect. Once I know the slope, that tells me how to orient the line segment. And there, that immediately traces the shape, right? Now, notice that what if the derivative is 2x, what could be the function? The function must be x squared plus some constant. Derivative of constant is 0. What's the meaning of that constant? The idea is this, guys. You can shift the curve up or down, and because slopes are not capable of communicating how high those curves are built. They're just, for this x, it tells you this is the slope, and you can reconstruct many possible line segments with the same slope. So here is one, and the other one is parallel. Here is one, and the other one is parallel. You understand? Slope does not tell you, because if you know the slope of a line, you know the line up to parallel, up to being parallel. Are you with me? Very simple, guys. I mean, you think, oh, I don't know what it is. I'm just trying to show you how easy it is to think here, if you see what you're talking about. You understand what I'm saying then? That means, if I understood it, it means that once I've obtained the formula for a function whose derivative is equal to itself, and I know its value at 0, I know that there is no other possibility for e to the x. It must be e to the x, because e to the 0 is supposed to be 1. Right? That means that e to the x crosses that same formula. Example of what, Francis? It's like asking, you see, I'm saying that based on my DNA analysis, I know that I have a Francis. And you say, can we do an example of what? What do you want me to do? To clone you? This must be e to the x. Think about it, guys. You can do it. I know that. And look what it means, guys. I now have a way to figure out what is e. I just take 1 plus 1 plus 1/2 plus 1 over 3 factorial plus 1 over n factorial, and so on. And of course, if I don't want to add to infinity, all I have to do is just add up to some finite number. So here I decided to truncate at 1 over 5 factorial, and look what happens for e, right? I get approximately the number of 2.71. And now look what happens, guys. For 2.71, if I take it to this power minus 1, I get a number very close to 1. You understand? If you add more coefficients, you can play with your calculator. Add more coefficients, add 1 over 6 factorial, add something else, and your approximation will get better and better of 1. You see, everything kind of is coming together. Here, you see, here I actually carried out, look at it. I added a few more. I carried out 1 over 6 factorial. Now I get 2.718. If I do the same calculation with 2.718, look how nice and close it is to 1, even with this approximation. You understand? I actually entirely bypassed the limit, but I constructed a function that tells me how to pick the coefficient. Yes, the closer you get. So e will be the infinite sum of those coefficients. You see, guys, I hope the idea is getting into you. You see, it's not a difficult idea if you understand what I did. What did I do? There were not a lot of options to move. I know the function is differentiable and the derivative is not changing it, and at 0 it equals to 1. Why did I make it equal to 1 at 0? To make it go through the curve of e to the x, if such a curve exists. You understand what I mean, guys? There cannot be, if the curve e to the x exists, it must be exactly the same curve that I obtained with that infinite polynomial. That is somewhat clear with geometry. I hope you understand, because all I'm doing, guys, I think of a curve as a bunch of line segments connected to each other. Now, a line segment is fully determined by two things: by the slope and by the position. Right? I can make the line segment move up and down and keep the same slope. You see that? So this line segment has the same slope as this line segment. Right? That's why if the derivative is 2x, the function must be x squared plus a constant, because the constant means shifted up or shifted down. I cannot recover from the slope information exactly where on the y-axis this thing is positioned. Where does it cross the y-axis? But if I know where it crosses the y-axis, I know the full curve. Right? So when I say f of 0 equals to 1, that means where the curve crosses the y-axis. Remember, line is what? You can, if you know the y-intercept and you know the slope, you can recover the line. You can do the same for any curve. Clear? So simple. Okay, guys, so I will, if you want to, of course, I will show you how those ideas are useful. This is something optional. If you read binomial theorem or know it, I can show you that if I take this definition, the formula for e to the x plus y equals to e to the x times e to the y follows. You understand? Because even that exponential law can actually be derived once you establish this function. Right? The exponential law is not truly understood until you have this function, perhaps. You see? And here I show you how you multiply it and how you get the exponential laws. And here I basically go through the proof that this infinite polynomial behaves like an exponential function. It's very interesting, but I will not torture you with that. I hope you will torture yourself with that. Good? All right, guys. So playing with the derivative reveals surprising connections to the world at large. So here is an interesting problem. I hope you will enjoy it, right? It's a little bit about probability, and probability is about everything, guys. Right? And I can recommend a quantum mechanics book if you want to see how probability is about everything. So a good Russian man never goes a day without tea or alcohol. Consider the following drinking habit. Begin with a glass of tea and an identical glass of, let's say, rum. Take a sip from the cup of tea, pour in the rum to make the glass full again, mix the spiked tea thoroughly, and take a sip again. And you continue doing this until you have drunk the contents of both beakers. Good? Until you have drunk the contents of both beakers, the question is, what's the probability that the last molecule that you take in is a molecule of tea or of water, if you prefer? Okay, here is that situation, and we will try to understand what I mean by last molecule. Okay, so imagine for a moment that we begin with 3 molecules of tea and 3 molecules of alcohol. Good? So the way we're going to, now with 3 molecules, you imagine that each sip is a sampling of 1 molecule that you remove. Clear? The probability that you drink tea in this case as the last thing would be the probability that you either take you consume molecule 1 last, or molecule 2 last, or molecule 3 last. Yes? So what happens next? So the probability that you will consume a molecule of T is just probability of E1, probability of E2, probability of E3. You add them together. But by symmetry, it's 3 times the probability that you drink molecule 1 last. You understand, guys? So then you ask yourself, what's the probability molecule 1 survives the first time you take a drink? What's the probability that it's not selected? Each of those 3 are equally likely to be selected. The probability 1 is not selected is either 2 or 3 selected, which is 2/3. Are you with me? 2/3. So the probability of survival after first round is 2/3. Now, what's the probability of now once you sample that molecule, one from the alcohol beaker comes to replace it. I call it green because I don't really care about what other molecules are around. I just care that one is in there. What's the probability of surviving one more round? Two-thirds. So this is also 2/3. And what's the probability of surviving? And now look at it. After this round, one more molecule came to replace it. Now again, we have 3 molecules here. What's the probability of surviving another round? 2/3. And what's the probability of surviving the next round? Now look at it. After this, one molecule was removed, but there is nothing to replace it. Now it's 1/2. Yes? Now it's 1/2 to the situation. Now that's the probability that one survives. You understand? So altogether, you multiply probabilities. So the answer is, so far the answer is 2/3 cubed, right? 2/3 cubed. There is also a 2/3 here, by the way, right? So it should be 2/3 cubed times 2/3 times 1/2. You understand? I forgot to mention this removal, right? So there is every time you see an arrow, that's 2/3 until the very last arrow, which is here 1/2. Okay. Here is that situation: 2/3 times 2/3 times 2/3 times 2/3 times 1/2. And what we get is 2/3 cubed times 1/3. And therefore the probability that it's a molecule of water is just 3 times this probability. So it's really 2/3 cubed, which is 1 minus 1/3 cubed, right? Now, if you do the same thing with 4 molecules, what would happen, guys? With 4 molecules, let's actually draw the beakers, and I will be erasing them to help you see what happens. So with 4 beakers, now we have 4 molecules. Here is 1, 2, 3, 4. Here is 1, 2, 3, 4. What's the probability of surviving first round? Surviving, you see, it's not sampled. So the probability that molecule 1 survives first sampling. 3/4, you see, because either this or that is removed. So the first round survival is 3/4. Now there was a replacement. One molecule from here replaced. What's the probability of surviving again? 1 surviving, it's not picked. 3/4. Now, once it was sampled, it survived. Another molecule was removed. What's the probability of surviving again? 3/4. Yes? 3/4. Now here, another molecule was removed and replaced. What's the probability of surviving again? 3/4. Now be careful. Now there is, you see, that's it. It replaced. Now we have 4 molecules, but no replacements. So surviving again is 3/4. But now because there is nothing to replace molecules, so 1 disappeared. What's the probability of surviving now? What's the probability of surviving now? 2/3. What's the probability of surviving now? 1/2. Look what happens here, guys. So we have this number, and here we have a lot of cancellations, right? So we can cancel out 3, 3, 2, and 2, and we have this result. We have that the survival of molecule 1 for through to be the last molecule is 3 quarters to the power of 4 times 1/4. Now, if a molecule of water survives last, why was 3/4 cancelled? Well, look at it. 3/4, 2/3. So I could cancel out 3 and 3, 2/3 and 1/2. So 2 and 2 cancelled, 3 and 3 cancelled, and we have 1/4 here. Now that's the probability that molecule number 1 survived last. But if it's molecule of water, it could be that molecule 2 survived last, or molecule 3 survived last, or molecule 4 that survived last. Yes? Good. So what do we get? We get that the probability that I'm interested in with 4 molecules is 3/4 to the power of 4. But naturally, when you drink tea, the number of molecules is larger and larger, right? So if you have 5 molecules, can you guess what would be the probability if I do that with 5 molecules? What would the formula be for 5 molecules? 5 in each beaker, I mean. No, Robert, no 3/4. My 3/4, right? 5 molecules, it's always out of 5, right? That you remove. Yeah. So Humira, 4/5 to the power of 5. I hope you can see that, guys. Just play this game. 4/5 to the power of 5. What about P6? That would be what? Five over 6 to the power of 6. Yes? Are you with me, guys? So of course the number of molecules is going to be larger. You see, and if I look at the situation, I now see that I am forced to calculate this situation. So it's limit as n goes to infinity of n-1 divided by n to the power n. You agree? That's the limit I need to deal with. You see, it naturally comes to that limit because the number of molecules are billions. It's in the billions, right? So that means that it's very good, well estimated if I push the number of molecules to infinity with this example. Right? Now I need to figure out what this limit is equal to. We can actually bring this limit and write it as 1 minus 1 over n. Do you agree? Because simply just divide by n. Here it is, right? I said n minus 1 over n to the power of n. You can write it as, you divide into n, so it's 1 minus 1 over n to the power of n. You agree? Simple, right? Now, before I mention anybody, would anybody have a guess of what this limit equals to? You don't have to. It's I'm not saying it's an easy limit at all, but just I wonder if you look at it and if you had to answer it, what would you have said? What would you have said is the limit? Okay. Well, Zakaria E. Could it possibly be E? Probability is between 0 and 1, and E seems to be a number that is 2.7, etc. So it cannot be E. My question is, what's the limit? If you have an idea of, if you had to answer this limit, what would you have said? So here you go. So somebody says 1. What is 1e6? I don't understand what that means, Francis. All right, let's look at certain things, guys. Here is how you might, what I call playing with a derivative. Why is it so important for you to not just memorize shortcuts, but to really understand what this thing is doing, how much easier it makes it all. Okay, you ready? I'm going to say something that's pretty difficult. E to the power of x, well, but that's not a probability, that's just a function. Let's go, guys, and let's begin playing with the derivative. So let's go back to the definition of the derivative. We have that the derivative of f of x is f of x and f of 0 is 1. What does it mean in terms of the definition of the derivative? In terms of the definition, it means limit as h goes to 0 of f of x plus h minus f of x over h is f of x. If I take this ratio limit, I will get f of x. Are you with me? Now, when I take the limit, that's very similar to saying if h is very small, then this fraction is f of x, right? Limit is just saying just make the function smaller and smaller, just make h smaller and smaller and smaller. But if h is very small, you will not distinguish this ratio from the value of the function at x. Yes? And then look what I can do, guys. Then I can rearrange the formula. I can rearrange the formula and make f of x plus h approximately equal to f of x plus h times f of x, or 1 plus h times f of x, taking this formula. You understand? Just guys, so write it up, right from this stage to that stage. Make sure, I'm just going to wait 2 minutes at most to make sure that you can get this quickly. Without looking anywhere, take the limit and get it, solve for f of x plus h, you see? Roughly solve for f of x plus h, you can maybe still use this. You just drop the limit by saying h is small. Solve for f of x plus h. You understand what I asked, guys? Just solve for f of x plus h. I want to see that you can just do the basic algebra here. So yes, Humira, f of x times 1 plus h is what you are supposed to obtain. Understand, guys? I just asked you to obtain this formula. It's trivial, truly, right? Look at it. Here it's done. Look at it. Just multiply by h, then add f of x. So we have f of x plus h f of x. And what happens afterwards? Just factor out f of x. And you have 1 plus h f of x is f of x plus h. Are you ready, guys? Now the hard part. I told you there is no such thing as h, there is no such thing as x. Those are just symbols to indicate an idea. What does it mean? That means, look at it, I can think of it like this. F of a number is equal to 1 plus a small step, the number minus the small step. Are you with me? Look at it, what it means. Look at it, if I take this to be a number, then this is that same number minus the small step. Symbolically, I'm saying this. I'm saying that what is x? X is x plus h, and that's my number. If this is a number, then this is a number minus the step. You understand, guys? X is representing a number. H represents another small number. It's a step. So you see, you can read it. You can read it with x and h and therefore not understand anything, or you can just see what is this saying. This is saying that the function at some number is equal to 1 plus a small step times the previous number. And so in symbols, I can write it like this. I can say that f of x is approximately, I just changed the meaning of x. I said f of a number, 1 plus h, the number minus the step. You understand what I did, guys? I can do that because I can reassign meanings for, I mean, x stands for a number. I can just reassign meanings. Are you clear? So if you want to preserve that x, this can be said this is u, and what is this? Then this is u minus h. And I can just, instead of using u, I can use x again if I like. There is no problem. Right? So a lot of you are confused by that. And why are you confused by that? When you're confused by such things, that means you are not reading the meaning, you're just reading the symbols. Right? You need to train yourself to see the meaning. Good. Now this gives me a recursive process. Do you understand what it means? I can walk back towards 0 because f of 0 is 1. I'm going to walk back to 0. Are you ready? So how do I walk back to 0? So the interval from 0 to x, I will divide into many steps, into n steps, where n is a huge number. So divide this into 1,000,000 steps. If you take this interval and divide into 1,000,000 steps, each step would look like the previous point. It's barely noticeable, right? And if I divide even more, even better. So it means that f of x will be equal to 1 plus the x over n. That's one step. The function one step back, x minus x over n. Now I can look at it. You see, now from this, standing at this point, I can walk one step back. And if I walk one step back, I multiply by 1 plus that step, the function 2 steps back. Are you with me? You see, guys, what I'm saying is trivial if you just not confused by the symbols. I mean, what this is saying is, if I stand somewhere, I can figure out what's the value if I walk one step back. I just multiply 1 by the small step back times the function evaluated at the step back. So, well, careful, right? So look at it. So first I just consider it with finitely many steps, but many steps. Look what happens. In this fashion, what happens? In general, if I make n steps, it will end up being 1 plus x over n to the power of n, x minus n over xn, which will be a 0. I go to 0. Are you clear? The steps have to be very small. So that means that f of x is approximately 1 plus x over n to the power of n. And the smaller the steps, the larger the n, the more that's going to be correct. You see, guys, that's what I'm trying to say. You see, you cannot arrive at this if you don't think about the definition of the derivative. Right? If you memorize, it's completely useless. But if you understand such things, then you can think using those ideas. You can play with them. This is what we get. And that tells us that the limit as n goes to infinity of 1 plus x over n to the power of n, that ends up being e to the power of x. I arrive at that formula. I will derive it other ways, but this is very nice, very intuitive way. You see, just you see, if you think it's hard, you need to go back to the definition, just see how I obtained it. You understand? I obtained recursion. Right. So just to illustrate it one more time. You see, it's not going to work if you take very big steps. But imagine I take just 3 steps. So I begin at this x, and this is 0, right? So what is that step? That step is x divided by 3. So then what's the value of this function? It's f of x is approximately equal to the step 1 plus x over 3 times f of x minus x over 3. Yes? And now I look at this part. What does this part equal to? That part is approximately equal to 1 plus x over 3. And this, if you stand at this point, just multiply by 1 plus x over 3. And then move one step before. So it's x, this number minus x over 3. So it's minus 2x over 3. And then that's approximately, you see, this line and that line are supposed to be essentially equal. And then I have 1 plus x over 3 cubed times f of 0, which is 1. So that would just be 1 plus x over 3 cubed. But those steps are large. So the derivative tells me I have to take small steps. So that means 3 is not good. I should take a billionth of a step. You understand? And the bigger the step, the smaller, sorry, the step, the bigger the n, the smaller the step, the more accurate it is relative to the derivative. It follows from the derivative formula tells me that I can do that. Good. And I am able, you see, guys, without anything, I'm able to obtain this formula. Now, if you understand, calculate before we leave. Calculate A, B, C, and D. You can do it now very quickly. Look what this formula is saying. 1 plus x over n to the power of n is e to the x. So what is A? A is e to the 5, Christiana. You are absolutely right. A is e to the 5. What is B? What is B? What topic is this? It's derivatives, it's exponential functions, it's my notes. E to the minus 3, look at it, because it's 1 plus minus 3 over n to the n, right? So that would be e to the minus 3. What about this one, guys? This is the limit that we were interested in. Do you recognize it? That's the limit for the water, for the water and alcohol. E to the minus 1. So Zakaria, it's 1 over e. This is e to the minus 1. And this is e to the root 2. Good? Wonderful. Now, before you leave, guys, one last, you see, look how much I can obtain. Now, before you leave, of course, correct me if my spelling is wrong. I want to ask you this rather interesting question. Are you ready? So, in what type of school lesson do you learn the phrase, may I have a large container of coffee? For what class do you learn that? It's a what, when, where type of question. So you say English. Okay, Christiana says math. Do you know what it is, guys? It's never boring when I ask those questions, right? Look at it. 1, 2, 3. 1, 1, 2, 3, 4. Do you now understand what it is? Look at it again. 1, 2, 3. 1, 4, 1. 3, 1, 4, 1, 5. What is that? It is pi. Look at it. 3 letters, 1 letter, 3.1, 4, 1, 5. How many here? 1, 2, 3, 4, 5, 6, 7. So I think 9 to 6. You can remember, if you remember that sentence, you know a lot of digits for pi. Isn't it cool? It's the type of games you see. Okay, goodbye. Have a good one, or stay if you want to ask me questions.
Professor?
Yes.
I have a question. How do we access the recordings, like from Zoom?
Very simply, it's on YouTube. You can type my name, and if you go onto my website, it says if you don't find any links to the recording, go on the YouTube channel, write my name. Right. So you just go in YouTube, write. I'll show you actually. Okay, I'm gonna stop it, and I'm gonna stop the recording.